So I'm going to talk about some of the research going on in my group, the Climate and Earth System Dynamics group here at Stanford. Your phone? No worries. And just to acknowledge the members of the group, we currently have 4 grad students, including Chris, who you'll hear from, and Daniel, who's here somewhere. There he is. Okay. Welcome to Stanford, Daniel. We haven't talked in a while. And 3 postdocs and a research assistant. And we do a lot of high-performance computing, running climate model experiments on high-performance computing, both here at Stanford in the SEAS, the School of Earth Sciences Center for Energy and Environmental, Computational Energy and Environmental Sciences, Computational Earth and Environmental Sciences, sorry. And also at NCAR and TerraGrid and other off-site locations. So if you have questions about high-performance computing resources in general here on campus, let me know. All right, I think that's what I wanted to give for the overview. So one of the overlying hypotheses for a lot of the research in the group has to do with the role of fine-scale processes, the kinds of climate dynamics that shape the phenomena that most directly impact natural and human systems. And we're interested in how these climate processes vary at present, because there's a lot of impact from the climate system on us without any climate change at all, just from the chaotic variability in the climate system. And we're also interested in how these processes respond to changes in radiative forcing, such as increasing greenhouse gas concentrations. And we were told that you would all be familiar with climate change and the human role in climate change. So I'm going to skip over that for now. If you object to that stipulation, stand and scream now. Okay, excellent. Well, all right, if you got it from Chris, then I agree completely with whatever he said. So I guess I would argue, in terms of in addition just to the scientific interest, that understanding the role of the climate dynamics that really that shape these climate phenomena. So the local scale climate phenomena, very acute, short time scale events. Understanding how these processes respond to changes in radiative forcing is critical for decisions that are being made about climate change, both from the adaptation perspective in terms of what measures can be taken to adapt to climate change. We need to understand the climate changes at the spatial and temporal scales that most impact us, and also from the mitigation perspective. In this, the second of these, the mitigation domain gets a lot less attention in terms of understanding the dynamics of these events. But I think that, and we can talk about this separately if you want, but whether from the perspective of cap and trade or from a carbon tax, we really need to understand what the value of avoiding a unit of emissions is, and that value is really a product of the damage that's avoided, or potentially the benefit that's avoided, I suppose, in integrating that. And for that, we really need to understand the physical processes that most impact natural and human systems. So most of the work in the group is done using climate models, and I'm going to assume that you're familiar with these. But most of the climate model experiments that you see in the literature are performed using global climate models, general circulation models, and these are fundamentally based on the laws of physics, although we can't resolve all of the physics at all time and space scales for the entire globe. So there is quite a bit of what's called parameterization that's used. We can talk about that offline if you like. My group also does a lot of high-resolution climate modeling, and much of this is through nesting, where we nest a higher resolution grid within a global climate model. And this is very computationally expensive, but it allows us to get closer to the spatial and temporal scales that we know are important for natural and human systems. And we're doing this high resolution modeling over a number of regions of the globe. Chris is leading the work over Africa, Chris Skinner. And yeah, so I guess I'll try to think of what else I have in there, but I'll show some results for the US in a minute. So basically we take a global climate model and we nest over the region of interest at higher resolution. No one would nest if they were trying to address this problem in an ideal way. Okay, so nesting is not an end in and of itself. The problem is that we're computationally limited. In a few areas we're intellectually limited in terms of resolving the scales that we're interested in. But it's mostly, at this point, it's mostly computational limitations, so we have to, I don't want to say cut some corners, but we have to deal with the resources that we have available, and nesting is an efficient way. But we're certainly moving towards global high-resolution modeling as well. All right, so one question that we might be interested in is how quickly can severe climate change emerge as greenhouse gas concentrations increase? And if we look at the global temperature projections from the IPCC 2007 report, this is the A1B scenario, which was kind of at the point that this assessment was done was kind of the middle of the road of plausibility scenario. What you see in black is the historical global temperature record, and then the purple is the suite of calculations of temperature. And this is as an anomaly from the late 20th century baseline. And what we see is that the calculation of global mean temperature matches the historical record quite well, and then going forward into the future, in this scenario, we see increasing global mean temperature, and as we go further into the 21st century, the spread within these calculations with different models increases, and we can talk about that uncertainty if you want. So how many of you are aware of the Copenhagen Accord that was agreed upon? All right, so some. So the Copenhagen Accord came out of the COP 15 meeting in Copenhagen in December 2009, and it's an agreement essentially to the most prominent agreement is an acknowledgement that 2 degrees centigrade above the pre-industrial global mean temperature is a target that the world to which the world should aspire. And there are some statements about scientific agreement that are in the Accord, and I'll save my comments about the level of scientific agreement for a little later. But the point is that the world community has agreed on 2 degrees C above the pre-industrial as being a target to which world government should aspire. So the warming, I don't have the figure here, but the warming from the pre-industrial through the 20th century is on the order of 0.8 degrees C, and this is unconveniently these temperatures are above a later baseline, so the late 20th century. But you can add something on the order of 0.8 C to these numbers to get in your mind the anomaly above the pre-industrial baseline, but somewhere out in around 2040, we're crossing that 0.8 plus 1.2 threshold in this scenario. So bear that in mind. All right, so we have this question of how soon might severe temperature emerge, and so this is a figure from a paper that we published a couple months ago in Climatic Change, and what we're showing here is, I lost my season, sorry. The left is December, January, February, and the right is June, July, August. And what we're showing here is the date of permanent exceedance of the historical maximum seasonal temperature. So if we look back in the second half of the 20th century or the late 20th century, depending on, we've done it a few different ways. And we just find for each part of the planet the warmest season that occurred during that historical period. And then we just ask going forward, what is the last year in which there's a season that is cooler than that historical maximum? So you can think about these numbers as the last year in which that historical maximum was not exceeded. So always warmer than the historical maximum for every year after the years that are plotted here. And what you see is that in the tropics, this permanent emergence is very immediate, right? So somewhere prior to 2030 on this graph for the areas that are the darkest purple. And if you look at the U.S., we see that in the mid-century, we find the last, in this case, summer season that is cooler than the historical maximum. So the point of all these colors is that with relatively moderate warming over the next few decades, in this case, I'm showing the 50th percentile. So there's a 50% likelihood of moving into a permanent new heat regime where every season is hotter than the historical maximum that we're used to. So I'm not sounding any alarm bells. I want to be clear about that. But one piece of evidence that we could see substantial high-impact climate change in the near-term future. And this just shows what I was alluding to earlier, that over the next 3 decades, we're likely to see warming above 2 degrees C if the current population and GDP growth continue as they have. All right, so we might ask, what are the potential impacts of this kind of climate change? And that's one of the main foci of the group. And another paper that came out earlier this summer asked this question about the premium wine regions in the western U.S. And so we have a set of temperature screening criteria that are empirically based, so based on observations and some lab experiments from the literature of the temperature tolerances of premium wine grapes. And we simply ask, it's really very simple-minded. We just look at the temperature in each location in each year, and we ask whether or not these different temperature criteria are met or not. If they're met, we say, all right, it's suitable. If they're not met, then we say it's not suitable. So we can focus in. These are in the high-resolution simulations, and I can explain the details of those if you're interested. But we can look at individual counties. And if you look, for example, at Napa County, in this case, I'm showing the area that is suitable in the premium wine criteria. And we're going forward in time here from over the first 4 decades of the 21st century. And each of these dark lines shows the area that's suitable in a different level of temperature tolerance. And it's expressed as the percent departure from that temperature tolerance right there, the red temperature tolerance. And so what you see is if in Napa, over the next 3 decades, something on the order of a 50% decline in the suitable area, regardless of the level of temperature tolerance that one might believe that is possible in Napa. And if you Google this, you'll find that the Napa Valley Vintners Association does not believe in any of our temperature tolerances. That's official. It's an actual statement. And I have 1 minute left. All right, so one question one might ask is if we, within this 2 degrees C target, if we see the potential for high-impact climate change, why is 2 degrees C the target? I'll leave that unanswered at the moment. But on the other hand, and of particular relevance for this group, there are tremendous benefits of energy consumption. And as I'm sure you're aware, there's a tremendous gap in access to energy consumption globally. And I'm just replotting what others have plotted before me. But in this case, I'm plotting the per capita energy consumption on the x-axis in the top panel against the Human Development Index. So each dot is a country. And in this case, I'm using the consumption-based energy calculation from Davis and Caldera. And in the bottom, again, against the Human Development Index, but for per capita emissions, again, consumption-based emissions. And what you see is this logarithmic relationship with some interesting outliers that we can discuss. But there's a clear saturation at high consumption, potentially some negative effects that an econometrician could analyze. Whoa. I knew enlightenment was coming. I didn't know it was going to be during this talk, but there it is. All right. I've completely lost my focus in a really good way. All right, so the question I have is how do we ensure that everyone in every one of these countries has access to the level of energy resources that that is required for a minimum acceptable level of human well-being? And I realize that just those 4 or 5 words together, minimum level of acceptable well-being, is a whole question in and of itself. But we could say, what about if they had the access to energy resources that I have? So what I'm plotting in the top is just the change in global greenhouse gas emissions if we elevate everyone in all of the countries with a Human Development Index of less than 0.9. So that's throwing out the top 28 HDI countries. And we just set those top 28 countries to 0. So you and I and everyone else in the US and France and Germany and all the top 28 never emit anything ever again, and at least of CO2. And we just add up what the increase would be if we elevate everyone else in the world to our level. So here the US, that's our level right there, the red dot with the US and the arrow pointing to it. If we elevate everyone to that level, we're looking at an increase on the order of 17 USs. And you can see Japan, if we elevate to the level of Japan, it's less, but still substantial. And here's the map of where these, where the increase in emissions is concentrated. And the point that I just want to make in closing here is, from the energy perspective that, and the climate perspective, is that there really is an important nexus. And we can talk about the ethics, but I don't think that we can avoid the demand for increased human well-being. And as you know, there's a very small fraction of Earth's population using a very large fraction of Earth's energy resources. There's tremendous human poverty that results from that gap, from the energy poverty that most people in the world experience. And whether one agrees with the ethical perspective that every human is entitled to achieve a level of well-being, my view at least is that there's certainly a momentum towards pursuing that well-being. And so the real question to me is not how do we avoid climate change, but how do we ensure an acceptable level of well-being for all humans while not doing irreparable damage to the climate system and the natural and human systems that are influenced by it. So thank you.